Hello. This video will focus on calculating a limit using the limits law. Now, since we know the concept of the limits, we understand what limits means, we can focus on calculations. We will use some limit properties, some limit laws. Suppose that c is the constant and limit of the function f of x and g of x at a exist. Then we do have a few tools. Limit of the addition or subtraction of two functions is equivalent to the addition or subtraction of two limits. Limit of the constant is just a constant. Limit of the constant times a function is simply a limit of the function times the corresponding constant. We can pull out the constant in front of the limit. Limit of the product is product of two limits. Limit of the quotient is the quotient of two limits. With actually this one, we have to be careful, and the limit of the function from the denominator shouldn't be 0, because if it is 0, we have to do something else with the entire expression f of x over g of x. We have to simplify. Limit of the power function is simply a power of that limit. It's also useful tool and can simplify our work. And similar, the root, the nth root function, limit of the nth root is simply an nth root of the limit of this function. And everything, of course, is happening at a, near to a. Okay, what we have? We also have a really important property, and we call direct substitution property. If the function f is a polynomial or rational function, or I can say more general, continuous function, and if the number a is in the domain of the function, which means it's part of the values, of the x values, then then the limit of the function f of x as x approaches a, it's equal to f of a. That means I can simply say the limit is the same like the value. But hopefully we understand the concept and we know that they are not really the same. We probably remember a function x squared. This is y, this is x, this is my parabola x squared. And we would like to investigate the behavior near to 3. That means I would like to find a limit of the function x squared as x approaches 3 from the left or from the right hand side. Okay, that we can see we don't have this, it's empty dot. It's not a solid dot. That means the only thing that I have to do, I have to check how, if x is getting really close, extremely close to 3 from the left and from the right hand side, how function behaves. Okay? And we can see function is approaching that dot, and this dot we know that is on the level 9. But now, if I would like to find the exact value f of 3, of course it's 9. Okay? But we kind of understand, we understand that the blue 9 is totally different than the green 9. Green, it's a limit. Function is approaching that height, that level of the function. Blue is the exact point. We are exactly at 3. Okay? But from calculation point of view, from arithmetic point of view, this is 9 and this is 9. That's the reason that we do have this above property. That means if function is continuous, if the value 3 is in the domain, in order to calculate the limit, I can simply substitute number to the formula of the function and get the answer. But please always remember what this means. We are approaching 9 for this, we are at 9. Okay, let's see how we can use the direct substitution property. Yeah, like for example, actually this is my function. Limit of x squared as x approaches 3. I can simply substitute and I do have 9, and we know that this is correct. I can have any function. X cubed minus x squared plus 2, no denominators, no problems. Negative 2 is definitely in the domain. I can simply substitute. And I hope we can do the arithmetic. Negative 10. X root x, 9, substituting 9. Function is defined at 9. no problem. A rational function, x squared plus 1 all over 3 minus x, I can substitute 5, no problem, and get my answer. And that we can see, we can simply directly substitute. Cube root of x to the power of 5, and now we have to be careful because we know we do not really use the calculators for the calculus class because we have to focus on the concept and we have to be smart with our arithmetic. That means probably I will not just go this way because 8 to the power of 5 is quite big numbers and I will never know what is cube root of 32,768. But what I can do, I can pull out that power, that exponent 5 outside. And I believe I know cube root of 8. 2 to the power of 5, 32. That means please always try to use at the right moment the property of the limits. Example number 2. Okay, evaluate a limit as x approaches 1 of the function x squared minus 1 all over x minus 1. That's what we see. If I do the direct substitution, okay, I mean, first of all, I see that x equals to 1 is not in the domain. But we remember that's not a problem since we're not looking exactly at 1. We're looking at the values near to 1. Substituting 1, okay, I can actually do this. 1 squared minus 1, 1 minus 1, of course, is 0 over 0. Okay, that we do have a problem because we can't really have 0 in the denominator. And of course, we're getting 0 because of the domain. That's what we have to do. First of all, this is one thing, it's good because we substituting 1 to the function on the top and the bottom, numerator and denominator, we're getting 0. This means that these two polynomials has a common factor. At 1, they equals to the same value, 0. That means our job is to find that common factor, cancel out, and then possibly use the direct substitution. That means this will be the type of the expression of the function that after direct substitution we actually getting. That means we got 0 over 0. And again, what we have to do, we have to find a common factors sometimes. We have to cancel out, and then denominator is no longer 0. Because we may have 0 on the top, and please remember 0 over 2, for example, is 0. That's fine. Okay, if I will have 2 over 0, then we don't know. We have to investigate further. Or, of course, 0 over 0, we have to also investigate. That means, please remember, as soon as we have 0 in the denominator, we do have extra work to do. Okay, that means let's try to find a common factor, cancel out, and see what is the output. Okay. That means you probably see that it's easy to factor out the function from the top, x squared minus 1. It's factored out as a x minus 1 times x plus 1. And it's so nice because we see that 0, x minus 1, common factor, common 0, gone. And now I only have function x plus 1, and I can substitute 1. Okay? Instead of x, I will put 1, and the limit is 2. Okay, that means we can see this will be the job for us to simplify. That means for most of the limits, not all of the limits, but this is one kind, and this kind is 0 over 0. I can name this. I can use the shortcut and I can say 0 over 0. Please remember, most likely the answer is not 0. If we still have 0, if after simplifying, if we still have 0 on the numerator, then of course it is 0. But most likely it's not 0. Okay, I can do one thing. That means what we had, the function x squared minus 1 over x minus 1, and I simplify to this function x plus 1. That means everybody knows the linear function x plus 1 is simply a line with the slope 1 and x-intercept -1. But what's happened? This function is not defined at 1. Okay, that means at 1, function has actually a hole. Okay, I can use the blue color. But this hole, this dot, is on the level 2, because that's what we got from the limit. That means the limit is 2, but it's no value. It's the open dot. No value at 1, but the limit is 2. That we can see we did simplify the function, and the function is just x plus 1, but we have to remember still no value at 1. Even if this looks like the function with the value at 1, but this expression x plus 1 came from the original rational function. Okay, that's me. Let's try to calculate more limits. Before we do the calculation, I will suggest everyone to know all of these special product formulas, because they will be really helpful to find a common factors. That's we did use the first one. A squared minus b squared can be factored out as a plus b times a minus b. A plus b squared, we can expand like that. A minus b squared, we can expand like that. Cube, make sure that we know the cube, addition and subtraction. And a cube plus b cube can be factored out this way, and a cube minus b cube can be factored this way. That means you can pause the video, you can make the copy of all of these formulas. They are gonna be helpful. Evaluate a limit as x approaches 3, x of the function x minus 3 over x squared minus 9. I can definitely see that I have 3 minus 3 and 9 minus 9. This is my case, 0 over 0. And of course, because x is not defined at 3. But that's not a problem for the limit. Let's find the common factor, factor out, and get the answer. We can see denominator is easily factored out like that, x minus 3 over x plus 3, and that's my common 0, gone. 1 over 6. That means at 1 over 6, at 3, we will have an open dot, open circle, and the level will be 1 over 6. I can possibly draw this function, because this function, it's the rational function, 1 over x plus 3, is just hyperbola 1 over x, but shifted 3 units to the left. Okay. And then we do have this part, and we have this part. But at 3, we have an open dot. I can nicely draw. Okay, and this is it. That's the limit at 1 over 6. Okay, example number 4. Evaluate a limit at 1 of x cubed minus 1 over x squared minus 1. Of course, 1 minus 1 on the top, 1 minus 1 on the bottom, 0 over 0. That means we know how to factor out. This is x cubed minus 1 cubed, x squared minus 1 squared. Okay, that means we're using the formulas a cubed minus b cubed, and you can check the formulas on my previous slide, and a squared minus b squared. And factoring out, we see the common factor, no problem. Now the quantity 1 is welcome. We can substitute and get the finite number. And the same thing, at 1, I'm not gonna draw this function because it's quite complex, but the only thing that I know that at 1, whatever is the function, I will have a limit 3/2, no value. And I don't know, of course, I don't know exactly the rest of the function. Okay, another limit, x plus 2 over x cubed plus 8, x cubed plus 8, x cubed plus 8. We can simplify, but of course, substituting -2 cube, of course, is 0 over 0. We do have to find a common factor. X cubed plus 8 means x cubed plus 2 cubed. And then we can factor out, actually I can factor out for you my x, my a is x, my b is 2, that means x plus 2, and then x squared minus 2x and plus 2 squared, 4. Okay, that means I do have this. I see my common factor, x plus 2, x plus 2. Now I can substitute negative 2. Make sure that we substitute incorrectly, and it's 1 over 12. The limit at negative 2 is 1 over 12. Okay, we have another function, square root of x minus 5 over x minus 25. X approaches 25. As we can see, substituting 25, we're getting 5 minus 5, 0, 25 minus 25, 0, 0 over 0. Of course, 25 is not in the domain. That means now, since this is not really a polynomial, it's like a root function, we still have to simplify. And what we have, in order to simplify the root expression, we will multiply and divide numerator and denominator by the conjugate expression. Conjugate of the root expression. Conjugate expression is the same values, root x, 5, 5, but instead of subtraction, we will do addition. Always opposite sign. If this will be addition, then we have to do subtraction. That means that's the conjugate expressions. And let's multiply. And now what we will do, we will definitely simplify the conjugate expression. That means having a minus b, a plus b, because that's the conjugate expression. How can we FOIL really fast? We will square the first quantity, we will square the second quantity, and always minus between. If you FOIL, you will see the middle parts will be gone, will be cancelled out. Okay, that means let's see. Square root of x squared, it's x, if x is positive, of course. 5 squared is 25, and minus between them. And denominator, I will not distribute, because I know that x minus 25, this is my 0. And if I will distribute, I will lose that 0. I will spread out, and I can't. I have to keep it together. Okay, and now I see the 0 is gone, x minus 25 over x minus 25. And now I can substitute 25. 5 plus 5, then 1 over 10. Okay? That means please make sure that you will use the conjugate expression for simplifying a root function, root expressions. Okay, the same thing. I type the solution for you. That means you can go through. I will not explain this. It's exactly the same procedure. Multiplying by conjugate. Cancelling out the common 0 and substituting negative 4. Okay, another limit is limit at 0 of the function 3 plus x squared minus 9 over x. If we put 0, it's 0 over 0. This one, it's relatively easy. We have to just expand 3 plus x squared. And please remember, 3 plus x squared is, I mean, if you don't remember right away, you can simply FOIL. Okay? But this will be 9 plus 6x plus x squared. Okay? Let's expand this, minus 9. Now we see on the top the common factor x. Let's factor out x, and that's my 0. The x is gone, the 0 is gone. I can substitute 0 instead of the x which left in the formula, 6. The limit at 0 is 6. Similar thing, similar functions, but 2 plus x cubed. Also make sure that you know how to expand this using the formulas on the slide provided. You can cube the quantity multiplying 3 times. Okay. Or you can just remember the formula. Okay, 8 is gone. We have common factor x. and x is my 0, gone. Substituting 0, we're getting 12. Limit of this function at 0 is 12. Okay, another one. Function of 1 over 2 minus x minus half over x. Limit at 0. 0 is not in the domain. If we substitute 0, we're getting 0 over 0. We have to simplify, and this one is quite how can I say, complex fractions. We have too many fractions. We can definitely rewrite as a one single fraction, getting a common denominator on the top. And we also 2 is not in the domain. Yes, we can see because 2 minus 2 is 0. Okay, I see that my common denominator from the top is 2 times 2 minus x. That means I will multiply my each expression, the function from the top, and of course the function from the denominator. That means multiplying the first fraction times this expression. 2 minus x is gone, only 2 will stay. Multiplying half times this, we can see 2 is gone and only this will stay. Okay, I can remove this one because it's only for. In the denominator, I can simply copy everything together. Okay, distributing this negative, please note the x will become positive. 2 minus 2 is 0, and then that's my common factor x. That's what we were looking for. X is gone. And now I can substitute instead of x 0, 2 times 2 for 1/4. That we can see common denominator. What you can do, you can also just take this and find a common denominator, and then dividing by x means multiplying by 1 over x. Okay, that means you can also do this way, but you will end up with the same fraction. Okay, now let's look at this one. We do have a function, which is piecewise defined function, different formula for x greater than 9, different formula for x less than 9, no values at 1, at 9, no values at 9, and we still have to find a limit. That means this one, we will use one-sided limits. Limits from the right-hand side and limit from the left-hand side. On the right-hand side, we can see the formula square root of x minus 9 represents the right-hand side, and the left-hand side, this should be left-hand side, it's 18 minus 2x. Substituting 9, we actually getting 9 minus 9, 0, and 18 minus 2 times 9 is 18, is 0. That means both of the limits are 0, then the whole limit is 0. The limit is 0. But please remember, value is not defined. Value of the function is not defined, doesn't exist. Okay. We do have another property because we practice direct substitution. We also have something like squeeze theorem. That means, let's see. First of all, let's look at this. If function f of x has less than g of x when x is near a, except possibly a, of course, because we're not looking at a, we're looking at the near, like close to a, and the limit of f and g both exist as x approaches a, then if the function has this relation, the limit has also the same relation. Limit of the function f of x will be less or equal to limit of the function g of x at a, near to a. So now let's add additional thing. Okay, let's take a relation between three functions, f, g, and h. That means f is the lowest one, g is in the middle, h is the highest. Okay. Now let's pretend that the limit of the lowest and the highest value of the function actually, it's equal to L, it's the same. That means if the limit of f of x is exactly the same like limit of h of x, then the limit of the middle function is forced to be the same. Yeah, because it's like squeeze between these two functions. Yeah, we call squeeze theorem, or we can call sandwich theorem, or we can call pinching theorem. I think calculus textbooks, most likely, they provide the name squeeze theorem. And we can see this is a graphical explanation. Function f, the blue one, the lowest one, h, the top one, and something between. That means if blue and yellowish, meets, they have the same limit at a, everything what is between must have the same limit. And one of the functions that we're using this is actually this one, x squared times sine of 1 over x. Find a limit at 0. That means what I will do. First of all, x equals to 0 is not in the domain. Of course, we can't divide by 0. But we're not looking exactly at 0, we're looking at near to 0. That means what I will do. Of course, I can't really say because this will give me 0, but this one is undefined at 0. Right? That means 0 times something that is undefined, I don't know. I have to be really careful. We really have to investigate. Maybe this is 0, but I do have to have a proof. That's what I will do. I will start with the trigonometric function sine of 1 over x. The range, the values of the function sine of any angle is between -1 and 1. We know that. Now, each of these 3 parts, I will multiply by x squared. -1 times x squared, negative x squared, 1 times x squared, and the middle part times x squared. And now I will calculate a limit at 0, okay, as x approaches 0, x squared goes to 0 and negative x squared goes to 0. That means bingo. Both of the limits are the same. Everything what is between must have the same limit. Okay, that means the function in the middle between x squared times sine of 1 over x is 0 by squeezing this function between them, between two functions, by the squeeze theorem. Okay, that means this is 0. But we can see we really have to have a reason. We can't just say right away. And that's the graph. Positive parabola x squared, negative parabola x squared. We can see they meeting at 0, but we can't really see the pink function, the red function in the middle. It's not defined at 0. Okay, another part of another kind of function is the functions with the absolute value. We also have to know how to investigate the behavior near to a certain value. That's the definition. Absolute value of x is defined as a x, which means absolute value of the positive number if x is positive. Absolute value of positive number is just the same number. Let's say absolute value of 5, I can simply ignore absolute value. Now, if the quantity inside is negative, okay, we can see negative. Let's say -5. I can't just copy the same number. And that means, please remember, we can't simply ignore the absolute value. That's what I have to do. I can copy this number, but I have to put extra negative. Of course, we know right away that absolute value of -5, it's +5, but just in case if we have to keep the same quantity, that means we can copy this quantity and we have to put extra negative. And this is that extra negative. So please remember the whole quantity -x is actually positive because that x is negative. Negative and negative is positive. Right? That means that's how we have to rewrite an expression with absolute value without absolute value. Okay, evaluate a limit of absolute value of x at 0. I can even come back to my graph. Of course, at 0 is 0. I don't have to really do much. I can simply substitute substitute 0, which of course is even weird. It's just absolute value of 0. I kind of split, but we don't have to. 0, 0, we don't really have to do it. We can simply say 0. Okay, absolute value of x minus 3, as x goes to 4. Of course, the same thing. We don't have to really, we don't have absolute value of 1. We don't have any problems. The problem begins when we getting 0 in the denominator. Okay, I think I did from both sides, because what this means that always when we have absolute value, that's what I just said, we have to rewrite without the absolute value in order to simplify, in order to proceed further, to do something. Okay? But if it's simple like that, we can simply do it. Okay, that's me. Now, let's look at this one. Absolute value of x over x, and we have to investigate the behavior at 0. And you can probably see, okay, 0 is not in the domain. That means now we do have a problem. I can't just put 0 over 0. No. We have to find this common 0. And now please remember, it's not, we can't just simplify this. That's not right, because I have to rewrite without the absolute value. That's mean what I will do. I will, let me actually, I type the solution for you, but maybe I can write it down. We have to find the limit on the right-hand side, and we have to find the limit on the left-hand side. On the right-hand side means x is all, 0 from the right-hand side means we have positive values. That means absolute value of positive number is just positive number. X over x, 1. Great. Now, x, I can copy x from the denominator because that's not a problem. 0 from the left-hand side means negative numbers. That means quantity inside the absolute value, this quantity is negative. I have to make it positive. Okay, negative 1. That we can see both of the limits, one-sided limits, are different. That's the reason that the limit is undefined. And I do have the same solution. Okay? That means most likely, if we will get a limit at infinity, limit of the absolute value, because we do have limits at infinity too. That's another kind. Limit of the absolute value. Most likely we will ask you just to evaluate on one side, because it's fun to get a limit of on one side, because they not really exist on both sides together. Okay, let's maybe do right-hand side. Because I definitely from both sides the limit doesn't exist. Okay, that's what we will do. First of all, let's see what we have. 3 minus 3, 0. 6 minus 6, 0. We do have 0 over 0. Okay, we have to find a common factor. Limit as x goes to 3 from the right-hand side. I can factor out 2. Okay, nice. But now we have to be really careful, because x minus 3, this quantity could be negative or positive. If this quantity is positive, I can just leave it like that. I can cancel out, my answer is 2. But if this quantity is negative, I have to put extra negative, because negative and negative is making positive. That means let's investigate. This means x and x is approaching 3 from the right-hand side. Like let's say 3.1, 3.01, or 3.001. And if we will subtract 3, because that's what we're doing, we can see we can always get a number, tiny number, but positive. Positive, positive. Okay, that means this is positive. We don't have to do anything actually. Okay, and now I can cancel out. My answer is 2. Okay, that's mean limit from the right-hand side is 2. And I do have the left and the right-hand side, and we can see we have 2. On the left-hand side, the quantity will be negative, and we have to put negative, and the answer is negative. But also please note, not always the limits from the right-hand side will give me positive answer, or the limit from the left negative. No, we have to look at the function. Okay, let's try this one. Also, I can maybe add the side 5 from the right hand side. 15 minus 3x over absolute value x minus 5. Okay, that means now the same thing. It's 0 over 0. That means I don't have to 5 from the right hand side. 3, 5 minus x. And in the denominator, I have 5 minus x, but I have to investigate the sign. Okay? So let's see, that x is 5 from the right hand side, 5.1 or maybe 5.01, 5.001. And then we have 5 minus. And now we can see 5 minus 5.1, it's actually negative number. Negative number, negative number. All quantity, this quantity is negative. I have to make it positive. And then I'm simplifying my 0, and the answer is actually negative 3. That means, can you see this? From the right-hand side, limit from the right-hand side, but the answer is negative 3. Okay, a nice multiple choice question. We can probably try to eliminate some answers, but let's see what we have. Limit as x goes to 7 from the right-hand side, and the function is 14 minus 2x all over absolute value of 7 minus x. Okay, 0 over 0, and I have to investigate. That means if it's 0 over 0, and we will probably not have double zeros, that means I would say this is not a good answer. And the same this one. That means the ratio is 2, but positive or negative. We have to check this out. Okay, I will factor out 2, 7 minus x. And I do have 7 minus x, but I really have to investigate the sign. Okay, let's see. This is x, and x is 7 from the right-hand side. 7.1, 7.01, 7.001. Okay. 7 minus 7.1 is negative. 7 minus 7.01, it's smaller, but still negative, still negative. That means I have to put negative in front to make the positive. 0 is gone. My final answer is negative 2. Please, because the common mistake is to assume that the number is approaching value from the right-hand side, and then we assuming, oh, it's positive. No, it's actually negative. Okay, I do have some for the infinite limits, which we mentioned in the previous sections. I have kind of like informal notes. If you will have a fraction, and of course, this kind of looks like this one, but of course, everything is in terms of the limit. But if we will have a fraction, and my arithmetic will show me that I have to divide by small number, because it's not really 0, or it's always really, really tiny number, close to 0. That means 1 over small number, it's always big number, which means for us, 1 over 0 is infinity. The only thing is we have to remember to check the sign. Is the 0, the small number, positive or negative? If it's positive, it's positive infinity. If it's negative infinity. If the quantity on the top is, of course, positive. Okay, that means that's also good arithmetic tool. And let's see how can we incorporate this for the limits. That means now we don't have absolute value. Okay, but let's see what we have. Limit as x goes to 3 from the right-hand side. And the function is x plus 4 over x minus 3. That's mean what I see. By direct substitution, I have something like that. Okay, 7 is fine. Okay, but I do have 0. That means, first of all, this is not a type 0 over 0. No, we don't have a common factor. That's we can't find a common factor. Second of all, this is not 0, because having 0 in the denominator, we do have problem. It's not 0. But what it is, if I come back here, it's a number, 1 or 7, doesn't matter, over small number is a big number. That means this is, I'm dividing a constant number over small number. That means my answer will be big number. The only thing is I have to check the sign, positive or negative. That means 7, I don't really have to investigate 7 because that's fine, but 0. This one, I did substitute 3, but to be really exact, this is 3 from the right-hand side, which means 3.1, 3.01, 3.001. And then we're subtracting 3. That's we're getting 0, but we're getting positive number. That means this is positive infinity is the final answer. Okay. Oh, I think I typed my answer. Okay, I can erase my writing. I can keep my typing. Okay, that we can see how we can investigate. I can actually put 0.1 just in case. Okay, that we can see. Please remember that's the next type. Okay, x minus 1, 6 minus x, and the limit is at 6. 6 is not in the domain, but we have to find a limit on the right-hand side. That means what we will do, I will substitute 6. 6 minus 6 is 0. That means my answer will be 5 over, but let's check that sign. Okay, this is 6 from the right-hand side, 6.1, 6.01, 6.001. And we can definitely see the quantity is negative. That's the reason that we do have negative. And it's negative infinity because of constant over negative 0. Okay, and I do have one more. Let's see. Limit as x goes to negative 2 from the left-hand side, x minus 3, 2 plus x. That means we can substitute negative 2. Actually, I don't like the 0. I will put 2 plus negative 2. Of course, it's 0, but we will investigate. Okay, that's mean now what we do, what we have. Let's investigate that 0. This is 0, but we will check what kind of 0. Actually, this number is not really negative 2. It's negative 2 from the left-hand side. For the negative numbers, we have to be really careful because this is the left-hand side, this is the right-hand side, and the number on the left-hand side is like negative 2.1, negative 2.01, and so on. That means this is negative 2.1. Okay, and adding, of course, means subtracting. That means 2 minus 2.01 is actually a negative number. Okay, that's what we can see. We do have this negative number. But now we have additional thing. The sign on the top is also negative. That means please take this as an account, under the account, doing your arithmetic, negative over negative is positive. And as we can see, it's just extra thing because this sign, the number doesn't matter, 5, 6, 1, but the sign, if it's negative or positive, it matters because it will change for the opposite sign of my infinity. That means I did cover a few types. Make sure that you know all of the types of these limits and good luck with your calculation of the limits. Thank you.